Now, let's look at another sorting algorithm, SelectionSort algorithm. Sorting array. Sorting, like searching, is also a common task in computer programming. Many different algorithms have been developed for sorting. This section introduces two simple, intuitive sorting algorithms, SelectionSort and InsertionSort. We covered the InsertionSort already. Now let's look at the SelectionSort. SelectionSort finds the smallest number in the list and places it first. It then finds the smallest number in the remaining list and places it second, and so on until the list contains only a single number. So the way to do it is we start to look at the whole list, find the minima. So the step 1 is find the minima. Second, we try to swap it with the first item. So we swap it, and this item is considered to be a sorted list. Then we work on the remaining unsorted list, find the minima, and then swap to the first element of the remaining list. Then it becomes like this. Then we find the next smallest one in the remaining list, and then swap to the head of this remaining list. Then this one we find a minima, but we don't need to swap. Something like that to continue that until the whole list is sorted. So SelectionSort is based on finding minima, swap, finding minimum, swap, finding minimum, swap, finding minimum, and do nothing, finding minimum and swap, finding minimum and swap. That's the core of the SelectionSort. So from idea to solution, the head of the remaining list starting from 0 until the end of the list or array. Then we select the smallest list from the head to the end. And then we swap the smallest element with the head element. So the first one we sort on the whole list. Find the minimum, put on the head. And then we sort on the remaining list. Find the minimum and put on the head. And then continue so on and so forth to the end. And the whole array will be sorted. So the first step, we would expand to call a finding minimum. First, we set the head of the element as current minimum. Then we traverse through the whole remaining list. If the element is less than the current minimum, then we set the current minimum as the element. And we further expand it so that we also keep track of the minimum index. So if we found an element smaller to the current minimum, we also keep track of its minimum index. And after that, we do swapping. If we found the minimum and we know that the current minimum index is not the head element, then we swap the head element with the current minimum index. So the whole algorithm can be written down in Java like this. So if we analyze the selection algorithm, we can find out it's a 2D algorithm. For the number of comparison is n1 for the first iteration and n2 for the second iteration. So the total time complexity would be n-1 plus c and n-2 plus c and something like that. And when we sum them up, we will get this equation. So it is also a order of n squared algorithm in big O notation. So it's a quadratic time algorithm. And the quadratic algorithm grows quickly as the problem size increases. If you double the input size, the time for the algorithm will be quadruple. So this is considered not really trackable. Algorithms with two nested loops are often quadratic. So let's look at the BoolJ program. And before we do that, remember that InsertionSort.java, the core is a circular shifting. Each time we try to insert it and then using the circular shifting. SelectionSort is finding the minimum and swap. Now, let's look at the program for SelectionSort. For SelectionSort, we take in an array, a double type array list. And actually this double can be replaced by any other data type. We get started from I equals 0 to the list.length minus 1. That would be ending at the second to the last element. The reason why we would like to stop at the second to the last element is because that at the last run, if we only have the last element, and it is the largest number, there is nothing to do with the finding minimum and then swap. It is only one element. When we start an iteration, we save the current I indexed element to current minimum. That is the starting point for the current minimum. And find the minimum and the minimum index so that we can swap between the current minimum and the I location. And the I location's value already been saved to current minimum. So the current minimum, when they changed, will be swapped with the I location. That would be the current index I. For example, if I equals 0, we search from 1 to the end of the array. That's the rest of the array. And then find the minimum between 1 and the end of the array. And then pick a minimum in there. That minimum should be swapping with the I location. If at the end, the current index still be 0, then we will keep the 0's value without any swapping. And if not, then we will swap the current index element with the I index element. If I equals 1, then we start from 2 to the end of the array. Because the 0 part, we consider that as the sorted array, and 1 part, we consider that is the one to be swapped for this second run. And if I equals 2, then we start from 3 to the end of the array, and 0 and 1 consider as being sorted, and 2 is the one to be swapped. And we will continue that until I equals second to the last, and the second to the last, the I plus 1 will be the last one. And so we just pick the last one, need to be swapped, and we swap the last one and the second to the last one. That's the last run for this program. And that will finish the sorting for selection sort. And here is one example. We have such an array, and let's run it. As you can see right here, the minimum is minus 3.3 and the maximum is 5 and is well sorted. Thank you.